Hello everyone. Today I'm going to showing my research about toward a demand-oriented spatial planning framework for growing infrastructure, considering ecological and socio-economical aspects. My name is Leng Linyuan. Come from Tsinghua University School of Environment, PhD student of Professor Jia. I will introduce from the four parts. For background, in recent years, rapidly urbanization has led to increasing impervious areas and changing natural hydrological processes. A major strategy for enhancing the sustainability and the resilience of cities is the expansion of nature-based solutions, green infrastructure. Globally, many countries have adopted measures to actively promote GI application, which is commonly referred to as low-impact development, best management practices, and the smart city strategy. Evidence have shown that the specific location of GI implementation within a watershed is the most important factor that determine its effectiveness. So is GI being planned and sited in locations that enhance urban sustainability and resilience? Or is it being sited haphazardly or opportunistically? So we define the location of GI from two aspects. First, the demand of GI. Answering the question, which region is suitable for GI implementation, which means GI needs a place. And second, the demand for GI. Answering the question, where is the biggest demand for the benefits of GI, which means a place needs GI. However, no existing framework that designs GI from the perspective of a place needs GI, which calls technology rather than problem-oriented. Motivated by these practical concerns, we propose a demand-oriented spatial planning framework for GI. This framework includes 4 building blocks. Step 1 is driver pressure impact framework development. Step 2 is data-driven loading. Step 3 is regional comprehensive pressure visualization. Step 4 is management strategies. The 4 part will be introduced in the methodology part. With this framework, a more integrated process could help to ensure that multiple GI benefits are provided to areas of the city that needed the most. Second part, we will introduce the methodology of our study in detail. We use Suzhou City as the study site and analyze in 3 spatial scales. It is a provincial pilot smart city, which leads to GI has emerged as a planning priority, making it an interesting, timely, and appropriate case study city to examine and improve our methodology. The driver pressure state impact response framework has been particularly useful for analyzing coupled human and natural systems because it provides a relatively simple and generic structure for linking cause-effect relationships. In this study, we developed a GI spatial planning index system using this framework to model qualitative cause-effect relationships between regional features and GI benefits. And assumptions required for determining the relationships between indicators were taken from a review of related literature. Natural and social economic data were obtained from open source. as different data have different resolutions. The grid of the raster data were unified to a resolution of 1 kilometer square to ensure consistency. Then we transform data to a 0 to 1 interval by using minimal maximal normalization method. Spearman correlations were used to access changes in the trade-offs and the synergetic relationships between the driver indicators across scales. Self-organizing maps is a fascinating clustering tool based on a neural network for classifying highly dimensional datasets. It was used to capture different bundles of drivers at the 3 scales. At each scale of analysis, the sensitivity of the clustering results were explored by building 2 to 30 clusters, and the lowest dBi calculated were obtained for the optimal number of clusters. Then we developed a comprehensive pressure index to serve as an integrated index for identifying highly priority hotspots where GI is needed most. After obtaining the clustering results, the mean value of driver indicators for each cluster is used to calculate CPI through the spatial overlay of driver indicators using the linear combination and weighting them by entropy method. Entropy method is a kind of objective weighting method, which means to determine the index weight according to the information provided by the observed value of each index. Then we analyze the results from the Spearman correlations among driver indicators. We can see a significant positive relationships between pollutants such as total nitrogen and rainfall, soil permeability, and impervious cover. This relationship as well as can be seen between population density and healthcare accessibility. Land cost and nighttime light index. The trade-offs and synergies between drivers changed less in directions and more in strength across the 3 spatial scales. A trend of increasing synergies and the trade-off strength as the scale of observation increased was observed. This may be because the process of scale synthesis from small to large scale. Then we found the hotspots in southwestern and study region, which accounts for 23% to 47% of the study area in different scales. We also found that ecological pressure mainly depend on pollutant loads and the impervious cover. The bundled clusters were prone to spatial aggregation when the scale was closer. We compared the results with the locations of current Suzhou Smart City projects. The analysis provides initial evidence that GI is cited in high priority areas for ecological improvements and socio-economic benefits increase. The 3 scales should represent different levels of administrative governance of GI projects. The 1 kilometer square scale was chosen to represent the size scale, while fine and individual management of GI implementation occurred. The 100 kilometer square scale was chosen to represent the street scale, involving local landscape management. The street scale involving local landscape management The district scale was chosen because it is usually the basic scale for making spatial planning and management decisions for the landscape. Therefore, it can serve as a reference for GI planning for different levels throughout this world. From this research, we conclude that the meaning of the framework that first, it can assist local communities, planners, and agencies in identifying hotspots where GI is needed most, and enabling these decision makers to create GI plans that incorporate a wider range of socio-economic and environmental indicators. Second, it can serve as both an aid to support in finding a credible basis for decision at the early age of planning and as a research instrument to examine the locations of current GI projects that match the priority areas. Third, the method provides a sound basis for developing target governance of GI planning and provides a reference for future research at different scales. Thanks.
Okay, thanks, Leng Linyuan. So any questions as comments from our other experts?